Hello, everyone. I am Tim Meehan. I'm here with Arjun Gupta. We're both software engineers at Meta. And today we'll be talking about using Presto for long-running batch queries at Meta. So describing the motivation to use Presto for batch, some of the details on, like how that works at Meta, how we operate it, some details on challenges, how we're solving those challenges, and how we're looking at the future as we scale batch even larger. So a lot of exciting updates as a part of this talk. Great, so let's get started. So we'll start with our Presto batch setup, but before that, it's worthwhile to ask the question: why even use Presto for batch? So it's definitely probably not obvious to everyone. After all, Presto began as a interactive oriented system. So why would you want to do such a thing? And so I think like it boils down to ultimately the ease of use. And so using that same query that you use in interactive, using it in batch as well is very powerful. That means that you can kind of like real time, iteratively work on your queries, and see results at interactive rates, and then very quickly put that into a batch pipeline. So that ease of user experience is very powerful, and people really like that interoperability between interactive and batch. So that goes into like the interactive speed and efficiency as well. And then like another, I think, point to bring up about the efficiency is that Presto queries tend to use less CPU than other engines. And so the efficiency is also a very big reason, because for very large batch warehouses, batch clusters and warehouses, you tend to keep careful accounting of how much CPU you use, just because resources are scarce. So there's also further motivation to prefer Presto, just because it'll tend to use less CPU for a query than Spark. And then I think finally another one is that the SQL dialect, like that Presto uses, which is striving for ANSI SQL conformance, is very comfortable and familiar with folks. If you know Postgres, you know a lot of Presto SQL, and so like this familiarity of the SQL and sort of like the lack of surprises about its syntax is also very powerful, and people really prefer that. So I think like just to recap the kind of like the developer experience, because of the interactivity, the cost savings, and then also the familiarity of the interface, I think are all powerful motivators for why you would want to use Presto for batch. And then we'll get into later, some of the implications of that, such as, if you have two or more systems for batch, like how do you handle that? And, like we'll talk about that pretty in depth later. So moving on then, after we've established, like why you would want to use Presto and batch, we can talk about, kind of like the overall workflow types that exist within Meta. And so very, very broad strokes, but, we can picture it into kind of like two broad categories within our warehouse. There's other uses for Presto outside of our main warehouse, but within our warehouse, there's kind of like two uses. The first is interactive, and the second is batch. So interactive, we have like all the things that we know and love Presto for, which is UI queries, dashboards, Jupyter notebooks, things in general where humans are, like a human being is waiting for those results. It's something more or less we categorize this as interactive. And then for batch, we have, basically things that are dominated by what's called periodic workload. And so this often, sort of like manifests as batch ETL jobs. And then, to support this periodic workflow, we have two types of jobs, which is testing workload, and then backfill types of workload. So these are all kind of like, things in addition to the periodic workload that we use for maintenance. So like you need to be able to test your periodic workload before it goes out into production. So that's what the testing is for. And then backfill is for when you need to, fix a data correctness issue, or you need to add more data historically or correct data historically. That's what you would use backfill for. And then finally, there's other batch-like systems that aren't quite batch, like these kind of like go into this other bucket. One example is like a backgrounders in Tableau where, they periodically refresh, like the scheduled nature of that makes them better suited for batch. And then just to classify things further, like we have kind of like, two categories here. One is, dashboard. Within dashboards, we have, two broad categories. Someone is waiting for the results, and then, things that are, kind of like getting refreshed in the background. So, for the things that, someone's waiting for, we prioritize those higher, and then, like those automatically refresh things, we, like we put them in lower priority because there isn't necessarily someone waiting for that. Some examples of that could be like TV screens that have a dashboard hooked up to it, things like that. And then, like within interactive, there's, like resource groups are a very powerful tool. And, like one of the things that we're looking at is further classifying, like this thing of someone waiting into, kind of like more granular buckets. Going into the periodic workload, we have, three, a few broad categories. The first is critical workloads. So it's very time sensitive. We want the jobs to land as fast as possible. So that we call them critical. And then, typical batch workload where, most batch workload, like there's some degree of latency allowance there. We put that into the normal bucket. And so, we measure both of these categories to make sure that, like we're hitting good SLAs, and, meeting customer expectations there. And then the final bucket is just like good to have. This could be, sort of like optional backfills, elastic capacity, things of that nature. Okay, so that's kind of like a categorization of our batch workload and interactive workload. And so now we can kind of like get into the details of like how things flow and how things connect within the warehouse. So we do have like an internal tool to help with this, very similar to Airflow. And in fact, I think not much of the terminology is the same. So we do have like a Python-based tool that, developers, data engineers use to kind of like, develop these pipelines that power dashboards or power, dependent data. And then within this framework, Presto interacts within a couple of different what's called operators, which is really just kind of like code that executes Presto queries. The first is a general operator that allows for any Presto query to be executed and allows for a lot of flexibility. But then there's also the a separate operator that is used specifically for basically ETL jobs. The majority of these fall into this latter category, but sometimes additional flexibility is needed. And then there's also lots of other operators that we use, including Spark, MySQL, sending out an email, writing to a file, executing some arbitrary Python code, things of that nature. So then, sort of like our ETL job, like the inputs really are just kind of like the table and partition where we want to write the data. The create statement in case the table hasn't been created yet, we can idempotently create it, through the create statement. And then there's the select statement, which is really kind of like convert into, a select into, or insert into type of statement. And this is used to actually populate the data and perform the ETL. We link these together through dependencies. So these dependencies are tracked through, through that framework that I mentioned. In this case, we have in these purple buckets, we have data that's essentially dependent on upstream tables. And so what happens is that these purple jobs are not executed until the blue jobs have finished. So that means that you can create these really directed acyclic graphs of dependencies and like essentially wait until the data is available until upstream or downstream ETL needs to occur. And then at the end we see some other things happen. An email is sent that indicates that some data has been populated, and part of it we can move to MySQL. So that's one example of what a workflow might look like, and this can get to be very complicated, and there's visualization tools to help sort of like make sense of all these dependencies. So going back into kind of like we kind of touched upon this briefly, but there's a few different modes for how workload, like how this batch workload is executed. The first is production. This is like, verified, repeatable batch, batch ETL jobs. This accounts for the majority of the CPU, and this is essentially occurs either daily or hourly or weekly, according to some cadence. The next two we classify as ad hoc. So the first one, there's tester. Tester is used to test out new workflows to make sure that they're stable, that they actually work before they go into a pipeline. And then backfill is used to, sort of like, as I mentioned earlier, correct data correctness issues, refill data back to a certain time period, things of that nature. And so like the physical mechanics of it working are, we have a scheduler. The scheduler triggers a command to a container management system, which then launches a container, which executes some code that essentially pulls in the Presto client to actually execute the query. And then once again, I believe that this is all very, very similar to similar tools that exist in open source. So nothing, I think, too crazy about this. So like in terms of some special features that we found to be useful as we operate our batch clusters, the first is there's resource estimates. These are used, essentially the idea here is as workload runs, using this framework, this Python-based framework that I mentioned, you can note the returned results of the queries, CPU and memory. And you can sort of like categorize as the workflow runs, like what's the average of CPU utilization and memory. And so like this can be used to basically give t-shirt sizes to the queries that get executed. And so like if it has large memory, we'll note that it's a large memory query, and then make use of that information downstream through resource groups. And I'll explain that the details about the resource groups a little bit later, but high level, the idea is through resource estimates, what we can do is we can categorize queries so that we can use it to control concurrency. Queries that are considered small, either in terms of CPU or memory or runtime, we can execute much more of those. And the queries that are considered large, those queries tend to sort of like use up a lot of slots, either in terms of memory or CPU in Presto's resource management system. So we tend to limit the concurrency of those. So this basically helps to improve overall throughput and also increase the CPU utilization of these batch clusters. So that's a very important piece of infrastructure. And then also we have features to sort of like, enable or disable features in case like a query has failed. So this is particularly useful to see if, there's been, a session property that we would like to try out in our clusters. We're able to enable it and disable it based on, essentially if it failed the first time. So that's like a way that we can kind of like experiment without, necessarily kind of like we can experiment with greater assurance. All right, moving on to how we set up our clusters. It's sort of like a very familiar horizontal scale out, and kind of like the various components here are all the way on the right. We have these boxes that represent Presto clusters. So we have in this example 2 Presto clusters that are set aside for interactive use cases, and then three set aside for batch use cases. The Presto client knows which one to talk to through this process that's called the gateway. And prior Presto cons, we've talked about other components that folks have built, including Uber and Twitter, about Presto query routing. And also wanted to sort of like point out that Twitter's version has recently been open sourced by Chun-Soon Tang. So definitely be sure to check that out in the main Presto repo if you're interested in such a component. But going back into kind of like the flow is essentially the Presto client talks to the gateway, and then the gateway will redirect it to the appropriate cluster. And then depending on what kind of cluster we're talking to, or what kind of what kind of cluster we need, it'll either send it to interactive or batch. The way that it does that is each of these clusters sort of like advertises what it's available to take on. And so Like interactive clusters have a separate catalog from the batch clusters, which have a different catalog, same connector, but different catalog name. And in using that catalog name, like we essentially route it to the correct clusters. So this also kind of like leaves a great deal of flexibility. For whatever reason you need to have it execute interactive, you're able to do that. Likewise for batch, you also have the capability of doing that. So, and then just some more details, like obviously it's not just simple load balancing. We do, there are some additional heuristics. In particular, the queue size of the clusters are used, for load balancing purposes. There's also some internal infrastructure on, where physically the data is and where it needs to go. And that's also quite important, but a little bit specific and not very applicable out in the open. And so, like here, we have like a nice visualization of our resource groups, and this is a very important, component of batch reliability within Meta, because this sort of like enforces, sort of like, number one, it enforces fairness. So, like certain, sort of like partitions of data are given, a certain degree of concurrency, so that, one partition doesn't sort of overwhelm the cluster and, cause unavailability for different kinds of partitions. And then also it's a way to kind of like constrain, sort of like resource heavy queries so that we can improve the throughput. So we do all these things through resource groups. Like there's a lot more, I think, to talk about with resource groups. And if it's a feature you're interested, there's good public documentation. And it's a very powerful feature for, ensuring, things such as concurrency, minimum fairness, reliability, and also sort of like conveying expectations to customers as to like how many queries you can send and how fast you can send them, and how heavy they can be. So it's quite a versatile feature of Presto. So I think like this is kind of like how we operate Presto. Presto Batch Classic. Sort of like, or at least how we've historically operated it. So like there's been a lot of very important updates, but historically this is basically kind of how it's worked. But there's been like a lot of challenges with this approach. The first is, essentially the first problem is that Presto by design doesn't have isolation. So what I mean by that is that when queries execute, fragments within each of the workers, each of these kind of like is executed within a single Java virtual machine. So, failures, like there's noisy neighbor problems and failures that can spill over into other queries. So, like this is, I think, in contrast to other systems that have a fairly strict isolation batch, for example, Spark, where, sort of like this presents a challenge because, like by design, lacking isolation means that you may have more trouble, hitting, good CPU utilization and good predictability of the landing time. So that's one problem that I think, or one, historical challenges that we've had. And then the second is the lack of fault tolerance. And, we put a lot of work into the second category in the form of a couple of projects that we'll be mentioning. But like, in this historical context, fault tolerance is actually quite important for batch for reasons that we'll see a little bit later. And then because of this lack of isolation and fault tolerance, then that also makes it, kind of like difficult to use things like spot capacity, elastic capacity, things like that. And then I think like at a higher level, MPP resource management, Presto obviously can be, thought of as an MPP. Itself presents, I think, kind of like challenges. The first is, going back into that resource groups component, you do need to very carefully tune resource groups, with fault tolerance and isolation or not. Just because, some queries can take up, many different slots in a resource group. And once that slot is taken, that reduces concurrency for other queries. And so it's important to kind of like, make sure that there's good categorization going into it. And so, I think like a key part is restricting concurrency based on the type of the query and there, like, you kind of like need some investment to set that up properly to make sure that it works. So doable, but like it's just a cost that needs to be bared. Moving on to then resource management. So like resource management is concentrated in the coordinator in the Presto model, unlike sort of like the Spark model, where you can choose to make it so that like essentially the resource management or the coordination is disaggregated. So you can make it so that you have a new driver per query. So we've solved a lot of this through the disaggregate coordinators project. So now there's actually isolation. If a coordinator goes down or something happens to it, the blast radius is can be much lower now. But then I think like you still have the problem that it only scales as large as the coordinators can handle. So there's a limit there. And then traditionally, once again, we'll talk about how we've fixed this in the past, but like traditionally, streaming shuffle has itself presented problems for batch. Streaming shuffle is eager, which means that kind of like your whole query chain, like the chain of fragments, all eagerly try to use up memory all at the same time. And so like this presents challenges for making sure that things don't use more memory than they have available. Even with spilling, like we've put a lot of effort into spilling, spilling itself kind of like presents challenges in batch because yeah, you can sort of like solve that challenge through spilling, but then spilling itself introduces costs and overhead, makes your query slower, and then also like by making it slower, they tend to use up resource group slots longer. And so like there's for particularly for periodic workload, like there's this possibility, especially as you have ever growing data, that ever more percentages of your batch workload could sort of like be spilled, which means that you get lower throughput, lower performance, and that kind of ties into the problems related to lack of isolation. Because of this lack of isolation, this sort of like makes that like an expensive problem to solve. Moving on to batch SLOs. So batch, like as you scale up your batch warehouse, batch SLOs become important. It's how you measure, how you're meeting customer expectations and, how you're, how well you're doing, how efficient you are. So it's very important to have SLOs. And so, like if once you start to think about batch SLOs, and at Meta, as we were thinking about our batch SLOs, what we realized obviously is that predictability is the most important thing in batch. So things can retry, like there's an external that workflow management component will automatically retry queries. So that's not necessarily problematic, but the problem is really the predictability. So things can retry, but if they have to retry a few times, then that makes the landing of that data to be less predictable. And so by having it not landed on time, then that means that there's staleness issues and things to work around of that nature. So predictability is super important for batch. But the problem is that like there's certain challenges for predictability. So there's like, and these are kind of like the challenges that I mentioned earlier. So there's the lack of fault tolerance and the lack of isolation and the consistent performance under high load. All kind of like make that challenging. And then top this off, like you want to strive for high CPU utilization in batch, and like that can also be challenging given those constraints. So we'll talk briefly about Presto Unlimited, which is something that we worked on to help address some of these. And this is still available in the Presto code base and solves a lot of these challenges. So high level helps Presto scale beyond its current limitations. The way that it works is it checkpoints data in between stages on disk, and this could be disaggregated or co-located disk, but that checkpointing is kind of like what helps it scale. So using that checkpointing, we can do stage level retry, which is a form of fault tolerance. So we have added fault tolerance, and then also using that sort of like disaggregated shuffle, we're no longer bounded by the network capacity for shuffle, and so we can use a large number of partitions, like in the 4,000 range. So this really helped us with sort of like our batch reliability. It was a major help. But then also it kind of like presented its own challenges. The first being that there's still no resource isolation. So like there's still basically global UMs that could occur. So like that's still something that kind of like needs to be solved. That isn't a problem in other systems like Spark. This is something that could have been worked on, but sort of like at the present, there's just no finer grain failure recovery. So there's no individual task level recovery. It's just at the stage level. So the failure recovery granularity could be leave something to be desired. It doesn't scale so well for long running queries. This kind of like goes back into the MPP resource management. It was difficult to leverage for elastic compute use cases because of that lack of task level retry. And so, like it has better reliability and scalability than Presto for sure. But then, like there's still overall this low reliability, or, like the reliability could be improved for long running queries. And so like we wanted to handle those better, just because those tend to be very CPU heavy and they often could, have outsized importance. Like we wanted to basically scale with the data and scale with the needs. So and each of these problems really requires a data engineer to jump in and help to fix it. So we really wanted to kind of like fix this in a more strategic way. So that was kind of like my part of the talk. We'll move it on to Arjun, who will talk about kind of like the future of our batch strategy and where we're going, and talk about some of those details. So thank you.
Thanks, Tim. Hello, everyone. This is Arjun Gupta. I'm a software engineer in the batch compute team, and I've spent most of my career working on different distributed compute engines like Hive, Spark, and Presto in the past 7 years. I've been working on Presto and Spark for the last 1.5 years now, and today I will talk a bit about our vision for Presto and Spark, how we are using it within Meta for powering batch workloads, wins and challenges that we are seeing in production, and what is the future work planned in this space. So as Tim mentioned, Presto and Presto Unlimited both have their own set of limitations, which makes them unreliable for long-running workloads. We also offer Spark as the best compute engine, and a lot of times, users have to migrate their workload from Presto to Spark to solve their scalability issues. So there is a lot of confusion among our users around which engines to use. When users do choose Presto to process larger data sets, or when the data set grows naturally over time, they often hit a scalability wall and their queries start failing with memory errors. They also see regression in reliability and landing time, thereby reducing predictability of their pipelines. Now, users work around these scalability limitations by splitting their pipelines into multiple pipelines, which process small amount of data, but this requires manual effort, which is costly. Users also migrate from Presto to Spark to solve scalability issues. However, migration is a challenge due to the differences in dialect and semantics of the two compute engines. So in order to reduce our users' pain, we need to consolidate SQL dialect within the warehouse for both interactive and batch workload so that our users can focus more time on business logic rather than learning different SQL dialects. The system should be scalable and fault tolerant so that users don't have to spend too much time firefighting operational issues. And finally, we want to consolidate our efforts at a single place so that we can move faster and innovate. And this is where Presto and Spark comes into the picture. It provides Presto anti-SQL syntax for authoring both interactive and batch queries. It uses Spark as the execution backend and thus can scale very well. And finally, with a single consolidated interactive batch engine, we can just focus our engineering bandwidth into improving a single stack. So very high level, what is Presto and Spark? Presto and Spark is basically Presto code running as a library on the Spark backend system. So it is a hybrid architecture where the front end, which includes parser, analyzer, optimizer, and even physical operators come from Presto, while the backend, like scheduler and workers and resource management and fault tolerance capabilities, comes from Spark. Presto and Spark runs as a custom batch job on Spark clusters on a shared queue. From Spark perspective, it is just a regular Spark application. Presto and Spark is integrated with Spark at the RDD layer, which means that it inherits all Spark capabilities that RDD abstraction provides. And finally, it is not a translator. That is like we don't convert a query to Spark SQL and then run it on Spark. We use the entire Presto front end in Presto and Spark, which means that we get full 100% SQL compatibility with Presto. With its hybrid architecture, Presto and Spark brings in some amazing reliability features. Since it uses Spark as the execution backend, it inherits Spark's robust fault tolerance capabilities straight out of the box. Presto and Spark can perform a more granular failure recovery at task level. This means that if a worker task fails due to a transient issue, it will be restarted and retried again. Presto and Spark also runs each worker in its own separate container, which are completely isolated from each other. This eliminates the noisy neighbor problem that Presto faces due to its multi-tenant execution model. There is no global memory limit in Presto and Spark. Local memory limits, they still apply, but with operator spilling enabled, we are able to scale better for long-running heavy queries. Now, enabling operator spilling in Presto and Spark is much easier and safer because each worker, it runs in its own isolated container. And thus, if a container ooms due to a bug in operator spilling logic or memory accounting, it does not impact other executing queries in the cluster. So this helps us in reducing query failures due to local or global memory limits. And finally, Presto and Spark, it leverages Spark shuffle capabilities for doing disk-based shuffles, which is more scalable than Presto's internal streaming shuffle. And this makes it possible to run shuffle-heavy queries reliably and efficiently in Presto and Spark. We do get some efficiency wins as well. Presto and Spark, it uses the same resource pool as Spark, which allows for better resource fungibility. We can leverage elastic capacity for Presto's long-running queries due to the improved task-level failure recovery that Presto and Spark provides. Meta's warehouse is moving toward low memory architecture, which means clusters are getting more and more memory bound. So as Presto and Spark, it uses disk-based shuffle and operator spilling, it's possible to run queries in low memory environment with very high reliability. And finally, you can throw a lot more horsepower on a single query by just increasing the number of executors or hash partition count, which can provide significant latency reduction for some CPU-intensive queries. So we have seen some really good wins as well for the workload that we migrated from Presto to Presto and Spark in production. We targeted long-running queries for migration, and these are the queries that run for more than 20 minutes, as these queries tend to be very unreliable on Presto. So after the migration, we saw failure rates, they came down by almost 3x, and wasted compute came down by almost 4x. We are also able to run 30% of the migrated workload on elastic capacity, which can be taken away from the cluster with very short notice. And we are seeing very good reliability for this workload as well. And finally, our users are very happy with this unified SQL experience that they get with Presto and Spark, as they can now write queries directly using a single dialect and do not have to worry much about scalability or migration. We have seen some challenges as well. So Presto and Spark, it uses Spark executor for running Presto code. And in Meta Spark's deployment, we do not share executors between queries for better isolation. So for every query and within each stage, executors are spawned up and released. Now, bootstrapping Presto worker on Spark executor is expensive, as we have to load all the connectors, plugins, etc. And we have seen that this can take around 15 to 30 seconds in just startup cost. Now, if executors are short-lived and we are spawning thousands of such executors for a query, the cost quickly aggregates and it becomes expensive. We are also seeing some problems in Presto and Spark, and this is mostly related to Presto's physical operator themselves. Even though Presto on Spark, it uses Spark backend, the operators running on Spark executors are Presto operators, and these operators are memory intensive. So we see OOMs happening in readers while reading wide complex column using ARIA scan, writers while writing dynamic partitions, in joins and aggregates due to key or partition skew, and even container OOMs due to memory accounting bugs. And so we are working on improving these areas of Presto on Spark to make it more performant and reliable, along with many other things that we'll cover in the next slide. So what are our future plans? So we are planning to invest heavily in the Presto on Spark stack to make it the batch compute engine within warehouse for all SQL workload. We are working on important features like adaptive query execution framework and related optimizations, which will help in dynamic planning and execution of Presto on Spark query. We are also investing in history-based optimizations, which will enable us to leverage historical stats of scheduled query for better planning. There is also work happening on automatically tuning hash partition count and executor count, which will help in improving query latency and CPU metrics. And finally, we are starting the effort toward integrating Presto on Spark with Velox, which is the C++ database acceleration library, and will make Presto on Spark more performant. So that's pretty much what we have for today. Thank you for joining our presentation.